Hello there. During this session I'm going to be talking about the birth of stars and where the energy comes from within stars. We're going to consider how stars are born through three different stages, and the picture here is interesting because it is the closest star forming region to us. It's actually, as we find out, in the Orion Nebula, or is the Orion Nebula, and in our galaxy it's the nearest location. It's only 1,500 light years away and appears in the constellation of Orion. So whenever you're looking at Orion and going, well, those are beautiful stars, well, one of these areas is our closest star forming region. Remember, nebula is the Latin word for cloud, and actually, as it happens, this is just a small part of a giant molecular cloud, which are thought to be the largest objects, features to be seen in our universe. So, where does this all begin? In a cloud? Well, what happens is we have these giant molecular clouds. So they're the most massive structures within a galaxy. They're about 100,000 to 1 million times as massive as the Sun. So there's a lot of mass there to do things. And actually defining them is very, very tricky. I was just going to say that there's a cloud of slightly more dense than the rest of space. To be that massive, they have to be pretty big, and obviously this is potentially from 60 to 150 light years in diameter, which shows why they're the most massive structures in the galaxy. And they tend to be mainly made up of hydrogen and helium, although there are some more complicated molecules to be found. And that's because of the increased density protects them from radiation of the stars, so some basic more complicated molecules can be produced. But generally these are known as giant molecular clouds. Now what happens is, from this giant molecular cloud, gravity will slowly pull the particles in a nebula together. Okay. Now, there's something called Jeans criterion, which identifies the density at which it is inevitable that the gravitational pressure will overcome the pressure of the gas and a star will form. So what we're saying is that there's a set density, and once a giant molecular cloud reaches this density, then it is inevitable stars will form. And as I mentioned previously, sometimes it takes a nudge, for instance a supernova, to knock a giant molecular cloud beyond this limit. Now, as they move inwards, the gravitational potential energy is converted to heat, and what is known as a protostar is formed. Okay. This is a hot ball of mass, but the heat only comes from gravitational potential energy being transformed due to the rubbing of all the particles together. Okay. It is only really, really, really massive stars which get hot enough in that stage, and they get hot enough to actually ionize hydrogen, and then the ionization of hydrogen can be seen, and this is known as an ultra-compact H2 region. Not important for the IB syllabus anywhere, happens to be one of the areas I specialized when I was doing my master's. So that's that. So we have a protostar. This is a large lump of hot gas collapsing on itself. Stage 2, and stage 3 is when we turn on the star. So that means that the gravitational collapse heats up the cloud enough, and at a certain point we get enough heat and we get enough density that the collision of the hydrogen atoms enables them to fuse and therefore release more energy, and then we have a self-fulfilling process. This fusion is often simplified as 4 protons banging into each other equals a helium nucleus plus energy. There are more complicated things going in, but that is at its most simple what happens. At that point, nuclear fusion happens, energy is being released, and a star is turned on, where it becomes part of the main sequence. There may be a little bit more of mass collapsing in on it, but not too much. So to look at this in a way which is more visual, we have what's known as the PP chain. Okay, so proton, 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 proton. They collide together, releasing a positron, and electrons which are around will annihilate, and they'll also release a deuteron, and that deuteron, which is just a proton and a neutron, combines with other protons, and they produce helium particles. Helium-3 and helium-3 combine to produce helium-4, and we note here that 2 further protons are produced. So therefore, this is a sustained reaction, and will keep on progressing without any outside help. Okay. So this energy, let's look at the energy a little bit more closely now. Going back to our nuclear unit, if we look at the mass of 4 protons compared to the mass of a helium nucleus, it means that we release 0.017 unified mass units of energy, which is 4.36746 times 10 to the minus 29 kilograms. Going back to Einstein's equation, E equals mc squared, we can then work out how much energy is released for each one of these fusions. So, some quick questions. How many kilograms of mass in 1 unified mass unit? That's something which you've just seen. How much energy is released by each hydrogen fusion? So that's the calculation I need you to use, using E equals mc squared. And if the sun had a luminosity of 3.8 times 10 to the 26 watts, how much mass is it losing per second? And then calculate how many fusions are happening per second in the sun. So these questions take you through step by step in working out how many fusions are taking place per second in the sun. So pause, work through that. The answers are 1.661 times 10 to the minus 27 kilograms in 1 unified mass unit. The amount of energy in that is 15.9 megaelectron volts, or 2.54 times 10 to the minus 12 joules. And that answer very much depends on what they state in the question. This means that if the sun is producing that much energy, it is losing 4.22 times 10 to the 9 kilograms per second, and that would require 2.48 times 10 to the 11 fusions. And that's happening per second, which I think is one of those great moments when you appreciate the magnitude and the amount of matter taking place in a star to allow that many fusions to take place at any moment, any second in time. So final recap. We have a giant molecular cloud, a dark cloud, and there's these dense cores. If they're greater than the gene criterion, which means they inevitably collapse, there's a gravitational collapse. Eventually we get a protostar, and what we see here is we have an accretion disk, and as well as gaining some mass, there's also what's known as a bipolar flow because of the rotation of the star. Then to maintain or conserve angular velocity, then we also find that we're losing some mass at the same time. As this continues, what we have is what's known as a protoplanetary disk, and what that means is that it's the disk where eventually the planets of our solar system will form. We'll have a pre-main sequence star. So what we have there is the star is just absorbing the final debris and leaving a planetary system behind, and then we have our central star is ignited with a set of planets rotating around, as we see with our sun and our solar system. So that's how stars are